Start this week's non-commutative. Okay, so we like to start this week's non-commutative geometry topology seminar. Here we have a newly arrived, more or less newly arrived postdoc, Suvrajit Bhattacharjee, who will be here for a year, and he's going to speak on braided quantum symmetries of graph C-star algebras.
Thank you, organizers, and in particular Karen and Ray, for this opportunity. I am indeed very happy to be here and speak finally. So finally is the important word. Okay, so the title is Braided Quantum Symmetries of Graph C-star Algebras. This is an almost finished joint work with Somal Jawardar and Shutanu Roy. So this is the outline of the talk. So I'll first define and give some examples of what these braided compact quantum groups are, and then we'll recall some basic definitions regarding them and recall the definition of a graph C-star algebra and what do we mean by braided symmetries of these graph C-star algebras. So then give another example of a braided compact quantum group, which is called the braided free unitary quantum group, and then finally compute what we mean by the braided symmetries of the example pooled algebra. So it will use the previous reconstruct the braided free unitary quantum group. Okay, that is more or less the outline. So we start with the following example. So suppose Q is a non-zero complex number. You take A to be the universal unital C-star algebra, which is generated by two generators alpha and gamma, subject to these relations. So they look a lot like similar to the usual SUQ2 relations and maybe succinctly written as this. So the relations one is also the relations are also equivalent to this metric being unitary. So the point is Q is not assumed to be a real number or between 0 and 1. It's taken to be an arbitrary non-zero complex number. So you can see if I take Q to be real, and then the mod Q square becomes Q square, and the 1, 2, 3, 4, the fourth relation becomes alpha gamma equal to Q gamma alpha, which are the precise relations for the functional algebra of the compact quantum group SUQ2. So if Q is real, then A is the algebra C of SUQ2. So let's see if we still keep Q to be real, then we know that there is a unique unital star homomorphism delta which goes from A to A tensor A. The tensor product is the minimal tensor product, such that the delta on the generators alpha and gamma is described in a precise manner, which is so you insert this matrix and so it's just forget the symbol, do the matrix multiplication and put the symbol tensor product, and then you get the relations 2. So this is a co-multiplication, which is we know to be co-associative and satisfies cancellation, in which case delta is called bisimplifiable, so that it defines a compact quantum group. The problem is, suppose now Q is not real, then the right hand side of 2 do not satisfy the, so recall that A is the universal C-star algebra generated by alpha and gamma satisfying some relations. So if we need to define a morphism from A towards the C-star algebra, we need some guys on the right hand side to satisfy the relation that is defining the C-star algebra A. The problem with Q non-real is that the right hand side of 2 do not satisfy the relations 1. So there is no morphism delta that satisfies 2. So that if Q is a purely complex number, a non-zero complex number, we cannot say whether it is a compact quantum group or is there even a bi-algebra structure. Surprisingly, so if we tweak this tensor product into so if we tweak the tensor product and introduce a new So tensor product, more precisely a monoidal structure on the category of sister algebras, depending on the parameter q by q bar, then so you formally replace the tensor product in the relation 2 by this box times sub zeta, and they satisfy the relations that define the algebra A, so that we really have a morphism delta from A to A, the braided tensor product with A, which also takes the form, the usual matrix co-multiplication form. So, so you have a new monoidal structure on the category of sister algebras, and it can be shown that the pair A comma delta satisfy the axioms for a CQG, a compact quantum group, but if you replace the tensor product with respect to the with the box times sub zeta. So what is this? So yes, so it is a star homomorphism, but Q is not real, so you would have Q bar appearing. It would not cancel out with each other. So that is why we need this adjustment. So this is zeta equal, so zeta is Q by Q bar. If Q is real, then zeta is 1 and it reduces to the usual tensor product. Okay, so this is the box times zeta is a special case of a more general construction. It is called the braided tensor product of two G sister algebras. So G is a quasi-triangular sister quantum group. So it is defined similarly as it is in the algebraic, purely algebraic case. So for the talk, I need G to be the circle group, in which case it is pretty simple to define everything. Okay, so it's just a reminder what a T sister algebra is. A T sister algebra is just a sister algebra with a T action. I have written it in a more with the quantum group flavor. So it's a unital sister algebra X. So a T sister algebra is a unital sister algebra X with a CT coaction rho X subject to the two conditions. So rho X is co-associative with respect to the co-multiplication on CT, which sends the generator Z to Z tensor Z, and it satisfies the Podlesh condition. So it is, so you take, so the rho X of X times 1x tensor C of T is the closed linear span of the product. So it is the whole thing, X tensor CT. And so if you have two T sister algebras, a morphism is a T equivalent one. So you have a unital star homomorphism from X to Y, which is also T equivalent. More precisely, it is, so you apply phi first, you then land inside Y and then apply the coaction on Y, which is rho Y. It is the same thing. If you apply the coaction on X first and then apply phi on the first component, you get the same thing. So this is what T equivalence means. So, and we denote more sub T xy for the set of all morphisms between the T sister algebras X and Y. This is a remark. So a T sister algebra comes equipped with a Z braiding, which is defined as follows. So Z is the generator of CT, the continuous function on the circle. So we call an element X inside big X homogeneous of degree n if the coaction on the element X looks like this. So it sends X to X tensor Z to the n. And we say that the element X inside big X has degree n, has homogeneous degree n. And for each n in Z, we take big X of n to be the set of all homogeneous elements of degree n. This collection Xn, where n runs over Z, enjoys the following. So each Xn for n in Z is a closed subspace of X. If you take two integers m and n, and you multiply two examples coming from X, two elements coming from Xm and Xn, they land inside Xm plus n. For each n, the joint of Xn is X of minus n, and take the algebraic direct sum of Xn's, it is dense in X. So we'll be heavily using this decomposition and the homogeneous degrees a lot. So now I proceed to define this tensor product box times zeta. So let us take two T-star algebras X and Y, where the coaction is denoted by rho with the superscript the algebra X and Y. Fix a scalar zeta which is in the circle, and let C of the T2 sub zeta is the non-commutative two torus, is the universal C-star algebra generated by two unitaries U and V, subject to the relation that V and U commute up to the scalar zeta. By the universality, there exist unique morphisms I1 and I2, which are unital star homomorphism from the circle to the torus, such that the I1 says the generator Z to U, and I2 sends the generator Z to V. And we use them in turn to define two new morphisms J1 and J2. The first one goes from X to the tensor product X times Y times C of T2 sub zeta, and J2 goes from Y to the same algebra. So J1 is defined as you first apply the coaction, and inside X tensor C of T, you embed it inside the tensor product X times Y times C of, CT, and then you apply the morphism I1 on C of T and land inside C of the torus. This is J1, and J2 is similarly defined. So we'll see in a moment why we need this stuff. So again, J1 and J2 is you apply the coaction, embed it, and then apply the morphism I1 and I2 correspondingly. You get J1 and J2. Okay. So now fix an X which is of homogeneous degree K. Then so J1 is you first apply the coaction so that X goes to X tensor Z to the K. Then embed, so I get X tensor the unit of Y and then Z to the K, and I apply I1 which sends Z to the K to U to the K. So J1X has this form, and similarly for a homogeneous element Y of degree L, I get that J2Y looks like this. Since U and V commute up to the scalar zeta, I get the commutation relation, which is 4, the equation number 4. So J2Y and J1X commute up to, again, a zeta power. So that if I take the closed linear span of these elements, the products of these elements, so the J2Y and J1X as a subspace, as a closed linear subspace of the bigger C-star algebra, they are the same. So J2Y, J1X is J1X, J2Y, which says that J1X and J2Y is indeed a C-star algebra. The braided tensor product is defined to be the C-star algebra. So I have taken two T C-star algebras and obtained a C-star algebra. So I need also a T structure on this C-star algebra, which is given by the lemma. So there is this unique coaction of the complex quantum group C of T on the braided tensor product X times Y, such that the morphism J1 that I defined in the previous slide becomes T equivalent, and the morphism J2 from Y also becomes T equivalent. So J1, so recall that when, so it's better to write X, so if you have, so in the ordinary case, so this is the embedding of X inside this guy, and similarly for Y, I should have something like this too. And this is J1. So it sends X to, yeah. So one can write J1X, one can write X box 1 instead of J1X. The point is here, X tensor 1 and 1 tensor Y is equal to, if you have, but here, if you have a 1 box Y, you introduce, to have the commutation, you introduce the zeta power for homogeneous X and Y, of course. So you introduce the power zeta to the LK, which is given by the equation 4. So this is J1X and this is J2Y. that is what equation 4 says. At the algebraic level, the coaction on the braided tensor product is that if you have x to be of homogeneous degree k and y to be of homogeneous degree L, then the product should have homogeneous degree of k plus L, and it is indeed that. Now, one more thing. So we know.
Question.
Yep.
Yeah, so basically, am I right that you are starting from the category of, say, co-representations of your quasi-triangular of algebra or compact group? Then here you explicitly constructed the braiding on this category, and then you just saying us that okay, we're considering two sister algebras in this category, and since it's a braided category, we should take a braided tensor product given by the braiding. So it's hidden in the formulas, but it's the classical from a braided model.
Yes.
Thank you very much.
So for the sister quantum group, you represent them on Hilbert spaces. So the braiding are on the Hilbert spaces. Then you have induced operators on the bounded operators. You embed the sister algebras inside those bounded operators, and you get the tensor product inside them. Yeah. So once we have the braided tensor product, the next thing is to look for how do I get the braided tensor product of morphisms. So that is what the lemma says. Suppose we have two equivalent morphisms, pi1 and pi2, growing from x1 to y1 and x2 to y2 respectively. So there is indeed a tensor product of them, which goes from the braided tensor product of x1 with x2 to the braided tensor product of y1 with y2, which is defined like it should be. So j1 x1, j2 x2 is the simple tensor x1 box x2, and you apply pi1 box pi2, and you should get pi1 of x1 box pi2 of x2, which is indeed the case. So this says, the lemma says, we can indeed get a braided tensor product of morphisms, T-equivalent morphisms. So I have a new, so there is, it can all be proved that the new monoidal structure is actually a monoidal structure. You indeed have the associativity constraints, the unit constraints, and it satisfies all the axioms. So it is really a new monoidal structure on the category of unital sister algebras with unital star homomorphisms. And a braided compact quantum group is a compact quantum group object inside the new monoidal category. So what do we mean by that? Is that, so it is a triple. It comes with a sister algebra, it comes with a T action and a morphism. So CG is a unital sister algebra, rho sub CG is the CT coaction on CG, such that the pair becomes an T sister algebra, so becomes an object of the category sister T. Delta G is a T equivalent morphism from the sister algebra CG to the tensor product of CG with itself, such that it satisfies the co-associativity and it satisfies bisimplifiability. So if you just formally replace the box times sub zeta by ordinary tensor product, you would recover the definition of a compact quantum group. And if the scalar zeta is identity or the T actions are trivial, you would indeed get a compact quantum group. So the first condition is exactly similar to the second, or in the case of ordinary compact quantum groups, the second condition. So there is this J2. I'm sorry. Yeah. So there is this J2 of C of G, which means I embed C of G in the second component. So this is really one box C of G. The second member is J1 of CG, which is CG box 1. And if you multiply stuff from delta G of CG, you get the whole thing, CG box CG. So the definition is really the same with the ordinary compact quantum group, but you replace the tensor product with this braided tensor product. Yep.
So here this
Yes. 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 Yeah. Yes. Yes. Everything is there. Yeah. Yes. Yes.
Question from Brown here. Is it well known that the data definition S3 times SC2 isn't the compact quantity, it's great compact quantity that we say it is e to the power 2 pi I k. It's well known that the data definition of S3, which is more than S2, isn't the compact quantum group. It's a braided compact quantum.
Is it? No.
Is it a braided compact quantum group? Say it's 2 pi I.
Okay. I don't know. No, yeah, I don't know. Okay. So with the definition, now I can state the theorem. So again, recall the algebra from the first slide. So Q was a non-zero complex number. Zeta is a scalar Q over Q bar. The algebra was generated by alpha and gamma, subject to all those relations where you put. So it was a SQ2 relation instead. So it is there, yeah. So this matrix is unitary. The following hold. So there is a unique T action on the algebra A, which say so it's defined in a way that alpha gets homogeneous degree 0 and gamma gets homogeneous degree 1. There is a T equivalent unital star homomorphism from A to the braided tensor product of A with itself, which satisfies the way we want it to act on alpha and gamma. So it sends, you see, if I apply a J here and the J here, and then formally multiply the matrix, you would get this the delta on alpha and gamma. So this is the thing I wanted, and moreover, the unital star homomorphism delta is co-associative and bisimplifiable in the previous sense. Thus, I have the three requirements to call A the coaction rho and delta a braided compact quantum group, and this is called the braided SUQ2, where Q is a non-zero complex number. This is the
comment.
So there's another comment from that. He says, I think it may literally be just this algebra for Q is equal to e to the pi I theta.
yes, yeah. Okay. Yeah, so it is called the braided SQ2. So and obviously, if you take Q to be real, then the zeta scalar, which was Q over Q bar, it is 1. So the action is trivial. Hence, you recover the minimal tensor product. So you get the ordinary quantum SU2. Okay. So in the compact quantum group case, they can be viewed as quantum symmetries of various structures, like many discrete structures, which are graph, finite one metric spaces, spectral triples, sister algebras equipped with orthogonal filtration, subfactors, so on. So our question was, can we view braided compact quantum groups as some sort of braided symmetries of some objects? In a recent preprint last year, Roy provided some examples of braided compact quantum groups which arise as braided symmetries in a precise sense, which can be defined for finite spaces. So finite dimensional commutative as well as non-commutative sister algebras. So we will be seeing that. So we could also produce examples of braided compact quantum groups that arise as braided symmetries of graph sister algebras. so which we now proceed to review. Also, there are, so we need a few more definitions before that we can do that. So once you have a braided compact quantum group, it is natural to ask how a braided compact quantum group acts on a T-star algebra. So it's similar to the case we had in ordinary compact quantum group case. So G is a braided compact quantum group. An action of G on a T-star algebra B is a T-equivalent morphism eta B, going from, it's a unital star homomorphism from B to the braided tensor product of B with CG, such that it satisfies co-associativity and the Portledge condition. Once you have an action of a braided compact quantum group on a T-star algebra, you can ask when I can call a state equivalent with respect to the action of G. So for that, we need the state to be T equivalent, which is defined as follows. So you apply, so F is a state from state on B, you apply, it is said to be T equivalent. So pick a little b from capital B, you apply the coaction of C of T on the element B, you land inside B of CT and then apply F on the first leg. You would get F of B times the identity of C of T. So this is called T equivalence. And if you replace T by G, it is G equivalence. So again, you apply the coaction of C of G on B, you would get inside B of box times C of G, and you apply for F on the first leg, you would get F of B times the unit. So I have cheated a bit because I defined that braided tensor product of two star homomorphisms, unital star homomorphisms, and F is not a star homomorphism, but the box of F and identity can also be defined. So by the procedure as follows, so we recall that the braided tensor product of B with CG is a subsystem algebra of B times CG times the torus. And so the F times identity is defined on this bigger sister algebra. So we take F box identity to be the restriction of that state on the subsister algebra. That is the restriction. So hence it makes sense to call a state G equivalent. Okay, so suppose I have an action of G on B. The action is said to be faithful if the star algebra generated by slicing the first leg of the coaction by all T equivalent state is norm dense inside the function algebra of the quantum group CG. Yeah, now, so this will be the class that we'll be looking at. So we'll be obtaining examples of braided compact quantum groups that arise as braided symmetries in a precise sense of this class of sister algebra. So we take E to be a graph. It consists of two sets, E0 and E1. E0 is called the set of vertices. E1 is called the set of edges. R and S are the row, the range and the source. The graph sister algebra, C star of E, is the universal sister algebra generated by families of projections and a family of partial isometries. So the projections are indexed by vertices and the partial isometries are indexed by edges, subject to this long list of relations. So for different vertices, the projections are orthogonal. For different edges, the partial isometries are orthogonal. If we take an edge E and first apply the partial, if we take an edge E, I apply the partial isometry SE and then come back with the joint of SE, I get the projection indexed by the range of E, and do the same thing in a reverse order. I get a projection, but I demand that it should be smaller than the projection indexed by the source at E. So for a vertex V is called regular if all those edges that start from V, the set of all those edges that start from V is finite and non-empty. So for regular vertices, I get that the sum of all those projections SE star, where E runs over the set of all vertices edges that start from V. This is also a projection because so it should be equal to the projection which is indexed by the vertex V. So the graph system algebra comes equipped with a T action. It is called the gauge action that gives PV the homogeneous degree 0 for all vertices and gives the partial isometry AC degree homogeneous degree 1 with so the E runs over the set of edges. Okay, so we now restrict the class a bit. So E is a finite directed graph without sinks. Sinks means that the set S inverse V, so fix a V, a vertex is called a sink if you take the set of all edges that start from V, and if that set is empty, we call it a sink. So we would not want sink, any sink. So I take E to be a finite directed graph without sinks. Since it is finite, the number of vertices is finite, which is m. The number of edges is also finite, which is n. And I take a n tuple of integers d1 through dn. The generalized gauge action is the T action on the system algebra that again gives PV the homogeneous degree 0 for all vertices V, but the partial isometry indexed by the edge EJ gets homogeneous degree DJ, where E1 and En is the entirety of edges of V. We need a few notations. So E is a finite directed graph without sink. There is a vertex matrix where the ijth entry is the number of edges between the ith and jth vertices. It is denoted by D, and the spectral radius of the vertex matrix is denoted by rho D. And we call again choose a subclass of the graphs. The graphs are called the graph satisfying condition dagger, which is the following. So the spectral radius rho D is an eigenvalue of the matrix D, such that there is an eigenvector with all entries non-negative. So this condition is needed because of the following fact, the second fact. So if I have a graph which is finite directed without sinks and satisfies the condition dagger, then there is a state canonically defined tau E. It takes value on S alpha S beta star. It becomes explicitly this, so delta alpha beta 1 over rho D to the mod alpha, and tau applied on the projection indexed by rho of alpha. So before that, C study is the closed linear span of these guys. So alpha and beta are paths in it, which means you just take consecutively edges and walk through them. They are called paths. And if you take the isometry, partial isometry S alpha corresponding to alpha and the adjoint of S beta, then the product actually linearly span the graph system algebra. So the second condition gives you, so obviously the collection of the linear span is dense, hence it makes sense to give tau E on these generators. So tau E on the element S alpha S beta star is explicitly given in these terms. So mod alpha is the length of the path alpha, how many edges does occur there, and R alpha is the, so alpha is a sequence of edges. So there is a last range which is called the range of the path alpha, and the symbol delta alpha beta has the obvious meaning. So when the paths are equal alpha and beta, it is 1, and if they're different, it is 0. The fact is the state just defined tau E, it is the equivalent for the generalized gauge action, so that it makes sense. So if we take braided compact quantum groups acting on the graph system algebra, then I can demand that the state tau will be equivalent with respect to the braided compact quantum group action. Okay. So suppose E is a finite directed graph without sinks and J is a braided compact quantum group. A G action eta, which is a unital star homomorphism from sister E to sister E box C of G, it is called linear if there exists a C of G valued n by n matrix Q, such that for each J, the coaction eta is very, so eta looks like this. So it sends Sj to Si, So J1 oops. This is really there is some. So the question is very specific and it sends Sj to a linear combination of these SIs. So if this happens, we call it a linear coaction of the braided compact quantum group G. And now with all these definitions, we can finally define what we mean by braided quantum symmetries. So we define a category. So given a finite directed graph without sinks that satisfies the condition dagger so that the state tau e exists, we define a category as follows. An object is a pair, it consists of a braided compact quantum group and a coaction. So G is a braided compact quantum group and eta is a coaction on the graph system algebra study that preserves the state tau e. It is linear and faithful. And so if we have two objects of the category C of E comma tau E, G1 comma eta 1, G2 and eta 2. So a morphism is a equivariant Hofstadter homomorphism from C of G2 to C of G1. It goes in. So at the group level, it goes from G1 to G2. When you get to the functional algebra level, it goes in the reverse direction such that it intertwines the two coactions. So you apply eta 2 first, get to C star E times C of G2 and then apply phi, you get eta 1. Yeah.
A very naive question from the categorical point of view. So when you, the condition 1, you have some braided quantum group. So it's a quantum group in some braided category, but your original graph system algebra not supposed to be an object in this category too, right?
It's a T-system algebra, yes, with the generalized gauge action.
So we work in this category.
T-system algebra.
Okay, so your G is fixed. Okay.
No, so the C-star algebra, C-star E is fixed, and I vary braided compact quantum groups that can act on C-star E. Yeah,
but then it will be braided compact groups with respect to braiding on T.
Yeah.
Okay. It's not general, it's very, very precise.
Yeah.
Okay, thanks.
Okay, yeah. So a terminal object of that category is called the braided quantum symmetry of the graph system algebra. So it's the largest braided compact quantum group that can act nicely. So it preserves the tau, it is linear and faithful, and it is denoted by aught of sister E together with the coaction eta E. And the theorem says that the braided quantum symmetry group indeed exists for a finite directed graph without sinks that satisfies condition dagger. Yeah, so this is the first theorem. I think I have some time to explain the proof, maybe a sketch of proof before that. So we would be needing the braided version of the free unitary quantum group. So if we recall, for an invertible matrix F, we can define the free unitary quantum group, which is the universal unital sister algebra that is generated by Uij's, such that you take the matrix U defined out of the Uij's, you demand that U is unitary and the conjugate matrix is equivalent to a unitary. Is the same definition, but we have to restrict the classes of the matrices F, so which I call admissible. So for an admissible matrix F inside the GLNC, you define the functional algebra of the braided free unitary quantum group to be the unital sister algebra with generators Uij, such that the two matrices U and F U bar sub xi F inverse are unitaries, where U is the matrix Uij and U bar xi is defined in the following way. So forget about the zeta stuff before. It's just U star Ij. If you remove the zeta part, it's the conjugate matrix. But since I have a T action involved, if you apply the co-multiplication, so you would expect that Uij goes under the co-multiplication to the matrix co-multiplication. So uik tensor ukj, where k runs over 1 through n, then u star ij, this matrix is not a co-representation. So so there again becomes a problem with the with some scalars. So you have to manage it with the entries u star ij. So that is the zeta power here. Okay, that's it. This is the functional algebra of the braided free unitary quantum group. So to say it to be a braided compact quantum group, we still need the three things. So I have got the sister algebra. It still remains to get the T action and the co-multiplication. Before that, some remarks. So since all the algebras have T actions, I have to restrict the class, which is the class of admissible F, and it takes a bit of time to say to write out the full definition, but it's not much restricted because all the matrices I would be needing for the rest of the talk are diagonal. Maybe so. The identity is admissible. The invertible diagonals are admissible, and these are the admissible F that I'd be needing. So there is a di appearing in the definition. That the interpol d1 through dn comes with such an admissible F. So it is hidden under the carpet. So an admissible F comes equipped with the interpol, so that u bar xi really makes sense. Okay, so now, yeah, this is the theorem. So there is a T action on the sister algebra just defined, and it provides uij with the homogeneous degree dj minus di for each ij. There is a unique unital star homomorphism that goes from the algebra to the algebra braided tensor product with itself, such that uij goes to the, so delta star is the usual matrix co-multiplication. So uik box times sub zeta ukj. I have written j1 and j2 instead of that. And furthermore, the unital star homomorphism is T equivariant, co-associative, and bisimplifiable, so that the sister algebra, the T action, and the co-multiplication actually gives you a braided compact quantum group. It is called the braided free unitary quantum group. And if you take zeta to be 1 or the action becomes trivial, you recover the free unitary quantum group for that F. And it's just a small notation. So if you take F to be the identity matrix, you write u plus n sub zeta. Okay. So the first step is to, it is. Yes, yes, yes. Yeah. It is. So u and f of the conjugate of f. So by requiring f of times u bar f inverse to be unitary, I say that u bar is equivalent to unitary, which is the case in the original case. But you have to tweak the conjugate here because you have T actions involved. It's exactly the same. So if you take zeta to be 1, you see the scalar vanishes, and if you take the action to be trivial, it also vanishes. So you actually recover the free unitary quantum group.
So does the value of zeta depend on the graph?
E.
Okay, does the value of zeta depend on the graph? No, I can take any parameter here. Okay, so as the name suggests, is the free quantum group. So more or less all the braided compact quantum groups with certain restrictions should be a quotient of this one. The first proposition says more or less a similar statement. So if you take an object from the desired category g comma eta, the eta being the coaction, then the underlying sister algebra C of G is a quotient sister algebra of the functional algebra of the braided free unitary quantum group for some diagonal f, so that I can explicitly manipulate with the generators uij. We define another category C prime E, which is, so before going to the definition, so let us recall how the homeomorphism group, for example, of a topological space is defined. So first you require that it is the collection of all those bijections such that F is compatible with the topology and F inverse is also compatible with the topology. So there is another way. I could have some set of homeomorphisms. For example, this is maybe it's just need only be a set of some homeomorphisms, and then the homeomorphism group is the largest one of the sets. And if you go big enough, then you also get the inverse, the composition, and so on. So the idea really is that you start with smaller subsets and look for the largest of those sets of homeomorphisms. So this category is precisely the same. So we look for the sets first and then get to the largest of the sets. So C prime E consists of triples X, rho X, and eta X. So X is a X rho X is a T-sister algebra, and it is very specific. It is generated by Tij. So one is defined required like this because of the previous proposition. So since T of G is a quotient sister algebra, Uij goes somewhere. So that is the Tij's, but that is the idea why I define X to be generated by Tij, such that T and T bar xi, so T is unitary and T bar xi is equivalent to a unitary. This is the first thing, and the second thing is eta X is a unital star homomorphism. I cannot speak of action of X yet because X is just a space now. But it makes sense to speak about space map. So eta X is just a space map such that it is very specific and it is given as we have seen in the definition of linearity. Okay, so and given to objects, a morphism is obviously from it is a unital star homomorphism which is furthermore T equivariant from X to Y such that it behaves nicely with etas. And the point is, in this category an initial object exists. So if you recall the category of quantum groups that act on the graph sister algebra, I demanded the quantum automorphism group to be a terminal object, and if you pass to the functional algebra level, it should be an initial object. The lemma says precisely it exists. So it is the smallest in some sense. U, rho u, and eta u. The generators are written box of uij. The T action is given as you would like, dj minus di, and the coaction or the quoted coaction eta u is also, so Sj goes to Si box Uij. The point is, it turns out that the initial object we just got can be provided with more structures so as to make it a braided compact quantum group. Like I said, so if you go big enough, you would get the actual homomorphism group. So the first step is so U is an object of the category C prime E. The first step is to observe that the braided tensor product of U with itself is also an object of the category. So the lemma says precisely that the braided tensor product of U with respect to with itself is also an object of the category as defined C prime E. So by the universality of U, you get a morphism for free which behaves in a natural way. So it sends box of Uij to the matrix co-multiplication, and it turns out that delta U is co-associative and bisimplifiable. Thus, there exists a braided compact quantum group GE such that the underlying sister algebra of the braided compact quantum group is U, the T action is rho U, and the co-multiplication is delta U just defined. Furthermore, it turns out that G acts linearly, faithfully, tau preservingly on the graph sister algebra C*, so that GE, eta E becomes an object of the desired category, and the theorem is it is precisely the automorphism group so defined of the graph sister algebra. So that settles the existence. We would now move on to the final part. So we compute the braided quantum symmetry of the specific example of the Kunz algebra. So it is the graph sister algebra of the n wedges of circles. So you have a single vertex and n loops. So it is explicitly the universal unital sister algebra, which is generated by SI. Partial isometries SI satisfies the relation. So ON also carries a generalized gauge action, which then provides each partial isometry with degree di, where d1 through dn is a interval of integers. So to look for which braided compact quantum groups actually act on the Kunz algebra, we needed to construct. So this is the very first braided compact quantum group that we needed to construct first, and then we tried to generalize the construction. So there is a unique unital star homomorphism eta going from ON to ON box, the function algebra of the free unitary quantum group for the identity matrix, such that it acts on a desired way. So Sj goes on to Si box Uij. Furthermore, this unital star homomorphism is equivariant, co-associative, and Podles condition that satisfies Podles condition. That means the braided free unitary quantum group U plus n sub zeta actually acts on the Kunz algebra, and the theorem is the braided quantum automorphism group of the Kunz algebra is this braided free unitary quantum group for the identity matrix of size n by n. So yeah, that is the theorem, and I think these are some references. So the first paper contained the definition of a braided compact quantum group for over a arbitrary quasi-triangular compact C-star quantum group. The second one is the one where the construction of the braided SU2 is contained, and the third one is Roy's paper that provides more examples of braided compact quantum groups that are universal in a sense for finite spaces. Yeah, I'm done. Thank you.
So, three questions from the audience.
So this dagger condition you had on the graphs about the eigenvectors, was it? So you wanted an eigenvector with all positive entries?
Non-negative, yeah.
So I was just, so if the graph is complete, I guess this is the Perrin-Frobenius theorem would give you this, is that right?
Yeah. It's the K-mesh state, so yeah.
I'm just wondering if there's like a description of in purely graph theoretic terms that would give this.
And there is so I think there is something called regular graphs, which I don't know. So for them, these states actually exist, and almost all the graphs you encounter are regular.
So regular means the degree is the same? Well,
probably. I really don't know.
Oh, okay, fair enough. And I guess another question I had was, I know you said all the graphs were finite, is that right? But I'm just wondering, like, if there's any possibility of making sense of this for O infinity.
Yes, but the problem would be that, so if it is not finite, the sister algebra is not unital anymore. So I have to extend the definition of existing. So we have only so far constructed symmetries of unital sister algebra. That means the underlying space is compact.
Yeah.
It just has infinitely many edges, not infinitely many verses.
Okay. Okay, then I have no idea. Yeah.
Fair enough.
Yeah.
Thanks.
Yeah.
Slide on the last slide before the references. Yes, over here, yeah, on the left-hand side of the isomorphism, last line. So the dependence on zeta is sitting inside of eta only, or else it's sitting inside of the automorphism. So the right-hand side depends on zeta. So everything incorporates this parameter.
No, so zeta is fixed always because you have the generalized gauge action on the Kunz algebra, which is so the degree SJs have degree di, which means that the coaction is z to the dj, and there is the zeta involved.
Yeah, so, okay, so and the question was the dependence on the left-hand side.
Yeah,
So the zeta is sitting inside of eta only.
yeah, yeah.
Yeah, also another big question is in this monoidal category that you have constructed, the unit object is still the same. It's just
Yeah.
a one-dimensional.
Yes.
Okay,
yes.
so tensoring with this thing doesn't do any additional twists.
No.
Okay.
So this tau e, I kind of let me a bit quickly, but it's some sort of KMS state.
Yes,
Is that correct?
yes.
Okay, and then this is where you're getting the zeta from, or does this?
Yes,
Yeah.
yeah.
So what about more general C-star algebras that are also have like a circle action and then
Yes, yes,
nice
yes.
KMS states and stuff?
Yeah, yeah. That would be interesting. Yeah. So the one obvious choice is to have, so for a CQG, you have the Voronovich character, which actually has a S1 action, and it also has modularity. So that would be the next step, but we don't know anything about that. Yeah.
So for example, like if you had a Kunz-Pinzer algebra, so this would have a circle action.
Maybe,
Any
yeah.
of these circle numbers that bring these and possibly
Yep. Yes.
Yeah, so I guess something like quantum S U2 should be a circle bundle over. It should be graph C-star. Yes, it is a graph C-star. And I believe it has it should be finite as well. So this should have, you should be able to make sense of this in that case.
Yeah.
Do you know what that is, or
No idea.
interesting?
Yeah.
Just that something like quantum S2. This has a definition for graph C-star algebra, and I'm pretty sure it has finite. It's finite.
Yeah.
Sure. Yeah, I guess it's the CPNs that are have big many edges. Yeah, but the circle bundles over CPNs, they always have finite. They're always finite.
Yeah.
Just C-star.
Okay. I have- yes. So if I will change my underlying composite triangle, how it's feasible to prove at least this length about the distance of the initial objects?
Yeah,
Or-
that is a question we have. So even if you do not change the underlying quantum group, but change the action, we don't know how it should behave. So all those functorialities should be checked. Yeah, at least seen. Yeah.
So it's not direct far from direct.
Yeah.
Oh, thanks. So I had a couple of questions. The first question. So in this case of graph C-star algebras, if you look at the braided quantum symmetry groups and vary zeta, and just look at the C-star algebras, do you necessarily get a continuous family of C-star algebras?
Yes, I
In
think.
zeta?
So, yeah. Yeah.
Okay. And then in this, so the second question then, are there any examples where you have a braided quantum symmetry group for some value of zeta, but not for others?
I don't know. We have not looked at it. Yeah, that's a good question. Yes.
Okay. All right. Thank you.
Yeah.
Just a sort of quick comment, I guess. There are these things called Smale spaces that are essentially higher dimensional versions of graph C-star algebras. or well, shifts of finite type, which need graphics rather than structure. Analog would be interesting to see if, first of all, if the quantum automorphism group of the graph that corresponds to the Smale space, if you look at the factor map, acts in this way on the Smale space structure.
Yeah, yeah.
More generally, to try to look at the quantum automorphism.
Yes,
It might
yes.
be a bit more difficult because then things aren't discrete anymore, but it would be interesting just to see if you have an actual.
Yes, yes, yes. That is actually very interesting. Shomal and I actually looked at those stuff, but from the ordinary point of view, not the braided compact quantum group. But we wanted it to entirely define it just like it is, not coming from any other way. So it seemed to be hard, yes, but it's very interesting. Yeah, it does carry an S1 action, those spaces.
If you take the not just the so there are these called well algebras.
Okay.
You take your stable groupoid C-star algebra and then the Smith space algebra. You do not work with the C-star algebra itself. Then you take the cross product.
Okay.
Those should be the analog.
Okay. Yeah, that's interesting.
The definition of the
Yep. Yeah, this one. Yeah, this is the.
No, even sorry, not for the graph, but in general, I guess. Where you were defining
Only for the graph.
only for the graph.
Yeah, it makes sense, but I would. So it makes sense for any C-star algebra. Would need the state. But it might not exist, obviously. Yeah.
question would be, the next question would be, like, do you have symmetries? You have braided symmetries of graphs, like more braided symmetries. So we're going to go with the idea which would be looking at something. We're going to classical quantum symmetry, which is more.
Yes, yes, yes.
Quantum symmetry, braided quantum symmetry. Does that happen?
Yes, because so SUQ2 doesn't for complex parameters, SUQ2 doesn't appear in the ordinary theory. So it was shown by Meyer and Roy that SUQ2 actually is a special case of a braided free orthogonal. We have obtained the braided free unitary here. So orthogonal would be a quotient of that. And yes, so we really hope that it would be a braided symmetry of some guy, because they really have appeared in the ordinary case. For example, SUQ2, I think, appears for the Podle sphere. So it is the quantum isometry group in the sense of Goswami and Momik. So they have indeed appeared. So the first thing we would be needing is that the action behaves well with the Dirac operator, and I have no idea what would be that. So the linearity condition is actually preserving the eigenspaces of the Dirac operator in a disguised sense. So that would be the first step. Yes. You, in a sense, you get more symmetries.
Just one final thing.
Yep.
So
This the zeta that you have here, is that related to the state, the constant that appears in the state in any way, or zeta could just be anything?
No, actually, zeta is the constant that appears.
Okay,
Comes
right.
with the tau e. Yeah.
Okay, and it's important that that it's us. Okay,
Yes,
right.
yes, yes.
Okay, okay, got you.
yeah, so it's the more questions to the audience, more questions online. So Thank you. Yeah, Suvrajit, yeah, we're ready to start.
Thank you.
So next week, we have Sophie Anna Nicholson from Gdańsk University for Odense, who's visiting here for 2 weeks, and will start actually in September as a postdoc. And she will speak about split extension KK equivalencies for quantum projective space. So yeah, we hope you all join us next week. And, thanks again.